We can go ahead and get started on that very pleasant note. Welcome to the very final week of the semester. For some, not all of you, your very final week here at Iowa State entirely. I was just attending some of the 492 presentations just before here, and it was nice to see some people who took this class 12 years ago who are there now as panelists for senior design. So even if you're graduating and leaving, you're always welcome to come back and contribute to the department any way you can. So this is our last week. There was a valid question on Discord about when our final scheduled exam time is, and it's a week from today. So it is next Tuesday. I think I mentioned I always have to double and triple check. I never trust it because you have to kind of look it up in a table and kind of cross-reference, but it is a week from today at 9:45. 9:45 to 11:45 is the time listed. I think we'll use a decent chunk of that time. I hinted at 15 to 20 minutes for your final presentation. Then we'll probably take a few minutes because what we'll be doing is, as you're giving your presentation, and I'll share the Google Doc and all that before the end of this week, you'll be putting up your rubric at the very end after you've kind of talked everything you want to talk about, demoed everything you wanted to demo for your project, and you'll kind of provide your own self-assessment as our team. Here's how we think we did on it. And, you don't have to be easy on yourself, you don't have to be hard on yourself, just provide an honest self-assessment of how you did on that. And then we'll take about 5 minutes for everyone who's then sitting in attendance, who's hopefully 100% of us on Tuesday, will then fill out a Qualtrics survey per team to also provide their individual assessment for that team. So you will fill out every survey except for the ones for your own team, and then I'll collect all those, include then, of course, my own assessment as well, and that'll make the entirety of your score for the project. Question? So if you look in Canvas, I don't have it open now, there is a submission box or a submission assignment for the final project. If I look at the description for it or the what to submit, it just basically says, submit what you think I need to be able to evaluate your project. So none of you promised as part of your rubrics that you were going to write up a final report. So you don't have to do that. Now, whether it's not a final report, but it's a really good README might also be helpful, right? So I'll be looking at it. I'll take a day or so probably to look, entirety of all the projects, and your job should be to make it so that I can kind of navigate what you're going to upload for that. Now, other teams, they have it all on a Git repository somewhere, and you don't need to upload anything, but some document that's going to allow me to just kind of navigate what you're providing. So not a formal report. I don't need 2-column IEEE proceedings format for what you're submitting. And you do have the slides, but assume that the slides themselves maybe aren't sufficient, or maybe you're just writing up that walkthrough of, okay, your own self-assessment, but the individual components you worked on and how things kind of worked out in the end for that. I listed that due date as Wednesday at the end of the night. That was kind of an accident, but I'm still okay with that. So the idea is that you are done by Tuesday. So your demo day, you are done. Your peer assessments will all be happening right there during that class. It's not something we do afterwards. I won't get to look at it until Thursday anyway of next week. So if there's something you want to tweak, you have another little bit more than 36 hours to kind of upload things into that Canvas window. That answer that. So I think README is the kind of nice way to think about what you're doing for that, because it is a little different than an MP in which there's like the highlighted portions of the assignments where here's exactly what I'm looking for in your write-up and in your code, and your job is to make that very straightforward that you've provided that. Here it's a little bit different, but in terms of your rubric, what are the artifacts you're providing? Don't just zip up the Vivado project and expect me to, or your project folder and expect me to kind of be able to navigate that very adeptly, so provide me some guidance for how to best. I think I've mentioned this, I'm very unlikely to ever build any of your code. First off, it's hard to provide it in such a format that someone can just take it and build it unless you have really good instructions for reproducing it. And secondly, I don't learn that much from it. So I trust your demos. I mean, I guess you could fake a demo. You could hook up your laptop to the other monitor and record. But we're not doing that. What's the point of doing that? So I trust your demos. So I don't need to run your code. I'm quite capable of generally inspecting the code and getting a good feel for what's happening with regards to your projects. So that's 1 week from today, which isn't a lot of time. So tomorrow's the last lab. And I asked Jeremy if he could come and be available in office hours, both last night. I don't know if he was there, and next Monday. He seems like he is available for it. But this is kind of go time. This is kind of it. Just kind of curious if you had to put a percentage where 100% is you're done and you're just waiting for Tuesday, and 0% is pure panic because you haven't started, which I know is nobody. How are we for the teams? How are we doing? So it's two different teams here. So.
I don't know. I feel like a comfortable 60, maybe 75%.
That's fine. I guess those are two different things. One would be, what score do you think you're getting if you had to submit it today, which I don't care as much about, but how are you for on path, 60, 70%?
Yeah, somewhere around there.
Seems fair. Okay. Other teams, how is Joel playing? She's just asking Joel. That's a good sign. Okay. Well. So as long as they're not doing -%, you're in good shape, right? As long as they're not actively making the project worse, it sounds like you're in pretty good shape. 60's okay. It's a busy time, though, is the only issue. You have other projects, other things you want to get done, so I understand that. But one more big push, and it sounds like we'll have something. I think everyone's going to want to have something that they can demo, right? And something that you're proud of at the end of the day. But we know it's always been about kind of compromise given limited time and resources this semester. And so, don't let the perfect be the enemy of good enough, right? And start to triage when it gets to be Monday night. What can we actually deliver for that? So I'll provide, just via some Canvas announcement, the slides link and the survey link we'll be using for Tuesday. But before the end of this week, I'll provide that. And then we'll just kind of step through them one by one. It's 4 projects. Even if I assume, you go to 20 minutes each, and even if we do take 5 minutes between each one to kind of provide some comments for your peer assessment, we should be able to get to all of them before the 2-hour time block is all used up. So let the rest of your team know to be here next Tuesday. That would be nice. I guess mandatory is probably the better word for it. So please do have them here and ready to go and prepared. I guess I talked about that at MP4 as well. You're not being graded on how great of a presentation you're giving. It's the same thing I'm seeing in senior design right now. Nowhere does it really say, or maybe it's just a few percent where it says quality of presentation. But the whole point of having a clear and high quality presentation is you can make your other points, is you can really explain what you're doing. And so we care about quality, not just for quality's sake, but because that's how we learn, that's how we understand what you are while working on. Other questions, or we can kind of move into this kind of bonus topic at this point with our prep week. This won't be on the final exam. Where we left off on Thursday, as we were starting to dive more into the architecture, and the architectural diagrams, at least as provided by NVIDIA, tend to look something like this. They don't show individual muxes and the wires and things like that. But I think given our even CPRE 381 level of microarchitectural knowledge, we can kind of get a feel to some extent what is happening here. Part of it is more of software limitations, and then the rest is kind of reading in between the lines in terms of what the underlying pipeline likely is going to look like. Now, NVIDIA has lots of kind of marketing that talks about how they are single instruction, multiple thread, versus what you would have at least in part learned about in 381, and to some extent we covered in this class of single instruction, multiple data. But when it comes down to the underlying microarchitecture, it is still SIMD. It's still single instruction, multiple data. Those are called streaming processors, later called CUDA cores, now just kind of referred to as floating point units, now that the marketing battle, I guess, has been won. And that is effectively all that they are. So it's for a single instruction, there's this potential multiple issue to multiple of these functional units being done in parallel. It does depend on the instruction. So a reasonable way to think about what's happening here is you have, although it would be floating point, you have a 381 style ALU implemented here. Your adds, subtracts, multiplies. Your basic operations are implemented there. In this diagram for this architecture in this generation, you could do 8 of them in a single cycle. Now you have other instructions we also need to have to be able to support, just like several of you are supporting for your projects. That gets kind of baked into this somewhat vaguely labeled special function unit that we're implementing here. And there'd be fewer of them. So there's a trade-off involved there. So it is still SIMD here, but maybe to a lesser extent. And there is no free lunch there as well. So there's a certain performance one can get out of basic just floating point instructions and the parallelization available there. And there is to then a lesser extent a certain amount of parallelism available when your application is using lots and lots of exponentiation and inverse square root and things of that nature in its code. But ultimately, what winds up then separating this from just a conventional SIMD style architecture, I would say there's two things. One is this restriction on your instruction streams and what they can look like. We see that when we look at it from like the software developer's perspective of you're writing this entire kernel from a single thread's perspective. And that's why we see a lot of that bookkeeping code in the kernel, so that each thread can kind of carve out based on its own index and ID that's provided for it, can carve out its own little subset of the total work that the application needs to get done. So that restriction is what allows the other main differentiating factor, which is really just that of scale, that this is SIMD type of architecture. When we go from Tesla series to Kepler series architecture and even then to today, primary difference is that of scale. It doesn't quite look the same, the color scheme's a little different in terms of how it's being marketed here. Those green boxes are your floating point units, your CUDA cores. Those yellowish boxes are your special function units. So there are some differences between the two. They're not exactly the same architecture, but the primary difference as we go from generation to generation is that of scale. It may or may not, and this is kind of where we left off on our discussion last Thursday, it may or may not influence how you write your code. From a forwards compatibility perspective, you don't have to change your code at all. Your code that was written in 2010 will generally still work on modern hardware. But then on the flip side, as you have much increasing scale in terms of the amount of parallelism on chip that's available to you, you probably then also want to rethink how you write your code. So you don't have to, but you probably would want to. Otherwise, though, when comparing the kind of initial general purpose GPU compute architectures to this kind of later and greater generation of it, primary difference is just a rebalancing of the compute resources that are available on chip. How many single precision units? And between those generations, it became important to also then have double precision units. How many special function units available here? This is the view of a single of these streaming multiprocessors. Maybe the color scheme makes it look more misleading than it is otherwise, but it is effectively the same exact diagram as in the previous one, just at a larger scale of what is available here. If we look at this otherwise, and if we think of this as just a large pool of compute resources that we're able to manage because we're all executing the same exact instruction streams, what else looks different in this diagram from, say, a 381 style processor? So that is a big difference. So let's not pretend that's a minor difference, but that is the fundamental difference. What else is different here from what you may have built, engineered, designed yourself? Schedules are definitely something we don't have to have support at all. And for 381 processor, you didn't do really any instruction scheduling at all. Modern microprocessors have a lot of instruction scheduling. This is something slightly different with regards to thread scheduling, so that is different. We'll talk about what that would mean in practice, although we'll stick with kind of high-level concepts versus microarchitecturally how it's implemented. Texture units are definitely different, but we kind of know what those are doing. Does anyone have any texture appearing on screen yet, or getting there? No? Okay. You got to be getting close, right? Even if it looks like garbage, it's still a texture. Even if it's mapped wrong, it's still a texture. But what we kind of know what those are doing now, right? Those are highly configurable load instructions with some filtering applied to the end result, right? Given a coordinate, give me a memory address, or multiple memory addresses, and average together the results in some way, shape, or form. So that is different, of course, but that we kind of understand. Instruction cache, data cache, for whatever reason it shows the size of the data cache, but not of the instruction cache. Modest instruction caches and data caches. We talked about that a little bit, but just to reiterate, you can get by with a relatively tiny instruction cache. for that same reason, that we have all these threads, but they're all kind of reading from the same instruction memory pool. You should get extremely good instruction cache performance because you're not just going all over the place. Everybody, if not entirely in lockstep, is roughly keeping up with each other and they're executing from the same pool of instructions. Likewise, for data cache, you can get by with relatively small amounts of data cache due to the SIMT model where we kind of overwhelm with threads and we just deal with having to sustain long off-chip memory latencies. So that, not so different. That's not so different. This is different, but we know what's different. This is different. What else is different then about this diagram? There was one more thing. Compared to what you would have built, part of it is really tiny.
I guess like having a separate load store.
Yeah, and if you could have, but that is usually not something that if it was a proper SIMD implementation, you wouldn't have had a parallelized load store unit. So that is different. You can think of load store as being another type of special function, meaning that these are optimized to do your floating point basic arithmetic as fast as possible. Every time you have to read from memory, well, things kind of slow down already. Just like every time you have to do sine of x, things kind of slow down a bit. So the other component here, not to belabor it because it's maybe more legible on my slide than what you can see on the screen here, is that register file. What's different about that register file from your MIB style register file? It's massive, right? Now in VHDL, if we kind of trust our synthesis tools, we just kind of tweak like the register count and it just synthesizes, but that is a massive register file, right? And maybe, it's a bit of semantics. When is something a register file and when is something a memory? Usually the implication is a register file has kind of individually addressable subcomponents here and potentially multiple parallel ports for reading and or writing. And that's kind of what we have here. But for those who can't read that, that's 64K 32-bit registers here. Now, of course, in modern CPU architectures, we don't limit ourselves to 32-bit registers anymore. Even if the ISAs themselves are potentially limited, we tend to have a virtual address space and we let different processes share the register file. But not to this extreme extent we have now in our GPUs. This is the other feature that allows us to scale to this particular size. Small instruction cache is fine. Small data cache we just kind of tolerate. To be able to allow these threads to execute in parallel, we then now have this I would say, utterly massive register file associated with each of these streaming multiprocessors. This is and 256 kilobytes in total. This is our limiting factor that we have here, but it's also what's really kind of unique to our GPU computing type of devices. So SIMT is like our SIMD, except we're kind of switching between threads relatively quickly. The other big difference is besides having a modest amount of on-chip memory, we have these relatively large register file. And I have a slide here that this is one way of having the programmer's view and visualizing what's happening in the register file. So when we say there's this many number of registers on that Kepler class device, that is an implementation decision, that is an architectural decision that is made that as programmers, unlike for the most part when writing conventional software code, we actually do have to be aware then of how many registers we have because it winds up being one of the limiting resources in terms of how much parallelism can we extract out of this device. So people were asking me last week, what is really different here? And this is one of the aspects I'd say is different than just doing conventional parallel programming, having to have a microarchitectural appreciation for what's ultimately happening under the hood. Now, to what extent do you need to have that appreciation? You probably can get by with 90% efficiency. If you want to get closer to that 100% efficiency, you do need to have this view of what's happening underneath the hood. This large register file gets statically partitioned at kernel launch time. It is based on subdividing it given each block of threads. And we didn't talk about it all that much, but let me just go back to this picture quickly to make sure we're still on the same page here. When I was talking about block of threads, that's one dimension of our kind of two-dimensional layout of threads here. We write each kernel from an individual thread's perspective. We allocate, we schedule and organize these threads via a 1, 2, or 3-dimensional layout of threads inside a block and a 1, 2, or 3-dimensional layouts of blocks inside that grid. And then in terms of how things are getting scheduled, they're getting scheduled on a block-by-block basis. The CUDA runtime scheduler is taking things into account such as the register count for that block, and it's determining how many blocks can I execute in parallel on a given processor at a given time. So that becomes one of the limiting resources for that reason. Let's skipping back ahead here, that you have 64K registers to work with, and then you also would have a certain number of registers that are required for each block to execute. Another way to think about how this register file would work in practice is that, again, you write your C code, it gets compiled to assembly, then some effective machine code here at the end of the day. It is written from a single thread's perspective. Think back to your MIPS days. So add R1, R2, R3, right? That's from a single thread's perspective. Hopefully that's not totally foreign concept to you, right? Destination register, two source registers. You look at CUDA assembly, it's exactly the same. It hasn't really changed at all. That's from a single thread's perspective. But now if I want to run 512 threads on this at a single time, I then have to do a static partitioning of that register file. So from each thread's perspective, it's R1 equals R2 plus R3 in my assembly code for the add instruction. But then they're each going to get effectively segmented off based on which thread they are and then consequently which block they are as well. So each block is going to get a chunk of this, and that's what's being kind of shown here. They're going to have the same amount of registers per block because there's the same number of threads per block, and then there's always going to be the same exact number of registers per thread here. It's kind of a logical partitioning of your register file effectively, where in theory every thread could potentially access every register within the register file, but as compiled down, that R1 equals R2 plus R3 gets compiled down to something like R1001 equals R1002 plus R1003. And the next thread gets R1004 equals R1005 plus R1006, and so forth. And the end result is this effectively static partitioning at kernel invocation at launch time of all the different blocks into their subsets of the entire register file. This can then have our implications on performance, which is why we want to care about it. There's 64K of those registers, and presumably you want to use as many as possible. Or another way to think about that is when you're launching your threads, you want to have as many of, apologies for kind of jumping around here, you want to have as many of these blocks be executable in parallel on the multiprocessor at any given time. And so you probably want your register layout to ultimately look something like this, something like that, where I'm going to launch 4 blocks at a given time on my multiprocessor, and I'm going to wind up using every single register. That seems like a lot, but it's really not a lot, right? That's 4 blocks. So each of them are getting 16K registers each, and we don't know how many threads are in the block. But if we assume there's 1K threads per block, then each thread is going to have exactly 16 registers associated with it, which you've written or you've looked at and played with assembly code. You've written assembly code. That's not a lot of registers, right? That's now just 16 registers. If I have 16 registers, I can fit 4 blocks on the GK110 device. Someone comes into your team, they make a one-line change, and now all of a sudden you're using 17 registers. Again, we don't usually explicitly allocate the registers, but you write CUDA code that then gets compiled to a certain number of registers that it's required to use. Make a one-line change, go from 16 to 17 registers. In almost all other contexts of computing, no big deal, right? But in going from 16 to 17 registers, this is an extreme kind of scenario, but in going from 16 to 17, we can now only fit 3 blocks on that device, and we're not using now a big chunk of the register file because it's 1,000 threads per block. It's now 17K registers per block. I can only use 51K of the 64K registers because I just can't fit another block onto that device. So why CUDA is hard, or why it can be hard, is not the mechanics of, once you've done it a few times, it's not the mechanics of writing CUDA code itself, not of writing a CUDA kernel for doing matrix multiplication. It's It's not trivial. You know, you have to have a deep enough understanding of the related programming language to not shoot yourself in the foot. You have to know how to do the CUDA-specific things that we're starting to approach here. Memory allocation can be a pain. Thread work partitioning can be itself a pain as well. So there's some pain points there, but it's not itself that foreign to us. Where you really can see the real benefits of doing CUDA, though, require having this understanding of what's happening in the system. So a whole separate kind of parallel task is, presumably, you get your code working. So it's like compiled and it runs and gets the correct result back out. Now, how do I determine if I'm in this scenario or if I'm in this scenario? And it's not just register files, as we'll see, there's other limiting factors. Trying to maximize efficiency as like a whole separate programming paradigm is pretty unique to these type of devices. It's not something we typically have to do when doing anything other than kind of HPC type of programming. So finally, I mentioned threads in our block, blocks in our grid. I looked at the video on Thursday, and I actually said that makes a 6-dimensional problem, but I can't do math properly. So it's 3-dimensional for threads in a block. It's 3-dimensional, up to 3-dimensional for blocks in a grid. That's 9-dimensional, and I said at least one 6-dimensional on Thursday. So it's 3 times 3, not 3 plus 3. So it's up to a 9-dimensional kind of layout of our threads for our problem that we're looking to solve. And then we have this scheduling of a block-by-block basis in terms of each streaming multiprocessor. And the other point that I mentioned on Thursday is once you've done that allocation of blocks, threads into a block, those blocks are pretty much entirely independent of each other. You organize your threads in a block based on the amount of coordination those threads may need to have. Although if they need a ton of coordination, it's not a very parallel problem. But if they need a small amount of coordination, that's all between threads inside a single block. Once we have blocks in a grid, we actually don't have much control at all about what order they're being executed in. And generally, any coordination there happens on a grid-by-grid basis. I finish the entire first kernel, that entire grid, then I do some coordination or synchronization, then I start that entire next grid there. So only within the block is there any kind of coordination here. That is the programmer's view of the thread model here. From an implementation perspective, and something that then is kind of a leaky abstraction that we have to deal with as the programmer as well, we have how the actual threads within a block are getting scheduled to the underlining microarchitectural pipeline here. Now, this is not something that NVIDIA documentation would really try to expose to you as like the programmer or user of the hardware. This is more of the academic attempt to, I don't know if reverse engineer is the right word for it, but basically model what is likely happening underneath the hood of a CUDA capable type of device. This is a diagram from GPU Sim, which is kind of difficult to use, but really still kind of best state of the art for simulating GPU microarchitecture. And this exposes that underlying scheduling mechanism by which we have this block of threads, and when it comes time to now execute those block of threads, at the microarchitectural level, they are collected 32 by 32 in what's referred to as a warp. So I already mentioned warps before. We saw the warp scheduler as part of that. Primarily, that's all you really have to think of it as. That given a certain number of threads in a block, presumably more than 32, so, let's say 1,024 threads in a block, in terms of how they're actually going to get executed in this sea of compute resources, they're going to be scheduled into groups of 32 threads at a time, and that's what's referred to as a warp. And that has some separate implications in terms of the underlying efficiency, because while it depends a little bit on which GPU generation we're talking about, still the basic mental model you want to have for your warps is they're going to be running entirely in lockstep with each other. And that will have some implications for performance. That is a microarchitectural decision. That's not sort of a CUDA decision. CUDA is how you manage how many total threads I have in the application, what kind of parallelism is available, how many blocks in our grid, and how many threads in our block. Underneath the hood, then, in terms of how it's being implemented and scheduled in this SIMT type of manner, those threads are getting grouped together in the block, 32 by 32. Generally, you can assume it does some kind of sequential grouping. I take the first 32, then I take the next 32, etc. And that is now, we can kind of see a little bit of what's happening here. That if I were to have an architecture with my 8 streaming processors or my 8 CUDA cores per SM, then if I had 32 threads, I would basically insert every 4 cycles an entire warp into that pipeline. Now, this diagram is, again, from sort of an academic kind of modeling / reverse engineering effort, but this is effectively, in terms of, if I told you you have to write the Verilog or VHDL for this is effectively what you would be building if you were building a streaming multiprocessor. It would be kind of a fun class in and of itself. You know, we wouldn't have cool graphics applications, so you'd miss out on the triangles, and I know you've all come to love our triangles. But it's also pretty manageable as well, given our resources. Now, when we look at what our streaming processes are, those green boxes, those SPs or CUDA cores on the prior diagrams, well, they're still here, but it's really a recognition of what are they ultimately. It's an 8-wide ALU. Or 8 ALUs in parallel, but that's effectively the same thing, right? It's a vector unit that is doing 8 operations potentially in parallel. Otherwise, you can kind of see what is very close to a conventional SIMD kind of architecture here. Instruction fetch. There's only one line being shown here. Well, why? Because we're scheduling this block of threads into this group of 32 threads, a warp at a time. They are all required to execute in lockstep. Not sometimes, not occasionally, not most likely, but always. They're required to run in lockstep. So there's just one line here because there just needs to be one instruction. Decode / register read, a bit of semantics here, whether that's one line or 8 line here. But certainly, even if it's one instruction, what did we just talk about? There's this kind of internal segmentation of the register file. So one of the threads in the warps gets add R1, R2, R3. The other one gets add R4, R5, R6, etc. So it's one instruction. Maybe the control signals are slightly differently because that's how we do our register read. But it's one instruction, one decoded opcode for that instruction, and then 8 sets of registers that are getting read for that. Here's where the actual then parallelism happens now, because now it's all add or floating fadd instruction. We do 8 of those additions in operation. If it wasn't an ALU type instruction, instead it was a memory instruction, here is where we would have our load store operation happening here, mem stage. And then we have our final write back stage here. And we know from implementation, that's kind of wrong, right? You know, we know that write back kind of doubles back into the register file, but effectively, logically, that's what's happening here. Underneath the hood, your GPU is a lot of your 3D1 projects kind of glued together, right? I mean, okay, this isn't showing all the muxes and things like that, but your 3D1 processor did effectively this, probably a scalar version of that, but just make more ports and you basically have the vectorized, or copy-paste your ALU, basically have the vectorized version of what's happening here. The other then wrinkle is this is showing 8-wide parallelism for this particular architecture. The warp size is either 32 or 64 in more recent architectures, but in this case it's 32. So we basically do this 4 times, and then that's executing one instruction for that warp. So every 4 cycles, we were able to insert a warp into that vectorized pipeline here, and we get all 32 threads to execute in lockstep. Where I'd love to go with this, and I don't think time's going to really let us get to this eventually, even as we use up Thursday, is what happens when you have an if instruction or a branch instruction in your CUDA, and you do. We have examples of that already. The whole point of having a branch is for things to make decisions, right? And consequently, what then happens if half the threads in a warp want to go left and half the threads in a warp want to go right? And that has started to change a little bit depending on how recent of a GPU architecture we're talking about. But for quite a period of time, the most straightforward explanation of what happens is you have a branch and you wind up taking both sides of the branch every single time. Because these warps are executing in lockstep with each other. I can't have 16 of the threads going here and 16 threads going over here. I can't even have 1 thread going over here and 31 threads going over here. So there's a couple different implementations that have been proposed and suggested how things are actually used. If it's a very short branch, you can implement something referred to as predicated execution. I'd love to get to that on Thursday. That we'll see if we get to it or not. In which you execute the instruction, you just don't use the results of the instruction. You kind of just waste the instructions time, but that keeps everybody in lockstep. Because otherwise, what then happens is we can no longer have this single kind of arrow here. We need everyone in that warp at least to be on the same exact program counter here. And that's what I'm referring to when I mentioned thread branching is supported inside a warp, but it's a lot less efficient than one would think. And the term that people would use, at least in the academic community, is sort of warp divergence, it's called. If you have all 32 threads in your warp doing different things, it will compile, it will execute, but you've basically entirely serialized your code. There's really no point in having that, because for all the different branches you may have inside your code, in order for this mechanism to still work, you basically have to execute all of those branches. I'll try to get to that a little bit on Thursday. The other part of this diagram that's critical that I already started to mention is, we have a relatively small data cache, and that's a design trade-off to just allocate more transistor budget to this, the ALU, than to this, the amount of cache you may have in a system. And we have then a cache hierarchy, but ultimately, if it's not available in the cache, you do have several hundreds of cycles of waiting for your DRAM to get the result back out. You maybe saw that when simulating or doing ILA for your own projects. Once it has to go off chip, you have to be very careful with how you're measuring your signals that you're collecting here, because you have to wait a long period of time. In this case, though, we solve this by not solving it, in a sense, that we have now, from a single warp's perspective, the story is bad. From a single thread's perspective or from a single warp's perspective, instruction read, fetch, instruction decode, execute, load/store instruction is what the warp or the individual thread is wanting to do. If it's a hit in the cache, all is good, we keep on going. If it's now a miss in the cache, we don't exactly give up, we just give up on that warp for the given period of time. That's if one thread in the warp misses in the cache, or if that's if all threads in a warp miss in the cache. If any of them miss in the cache, we then effectively allocate that warp or reallocate that warp as not being active at that period in time. So from that warp's perspective, that load instruction may in fact take more than like 500, 600 cycles, which is bad, right? That's very laggy, very high latency for that from that individual thread's perspective. We're feeling the full brunt of the memory hierarchy's latency from that individual thread's perspective. Why is that okay? And in this diagram showing it's not just that thread that has an issue, it's all some subset of these previous threads that are also currently waiting for the results to come back from DRAM. Now, there's high latency, there's very high throughput as well, so eventually they're going to get their requests resolved and get the results back through here. Why is that okay? It's because we don't necessarily care about the latency at all, or certainly the latency of an individual warp or an individual thread. We care about the total throughput of what's the amount of computation we're able to get out of this particular chip in a given period of time. So having that high latency is perfectly okay, and it's fundamental to this streaming model of doing our computation, as long as what? Based on this diagram, what do we see? Thread warp 5 is in trouble. It's on timeout. Why is that not potentially an issue? Other stuff. Other warps are still available. So when we talk about the kind of impossible to precisely answer question of how many threads is enough, or how should I try to parallelize this, more is within reason generally better. Fundamentally for this reason, as long as we always have one ready warp ready to go, we're as good as we can be, right? Those ALUs are always doing something in the streaming multiprocessor. We're always executing with the amount of resources we have to do computation on our chip. And it doesn't then ultimately matter how many of these warps are sitting here idle in timeout waiting to get the results from DRAM, as long as there's always something ready for us to go. That's not that straightforward because, right, we write code to read from memory and write to memory ultimately, and depends on what, reference you read, every 7th instruction is a load or every 10th instruction is a load. I mean, we do load a lot from memory. That's the whole point of reading from memory and doing our computation. So we do need to have enough of these that ultimately, even though from an individual warp perspective, that load's going to take 600 cycles, we're going to have enough of these available such that maybe by the time thread warp 2 has finally gotten its results from its load, we're running out of threads available for scheduling, but things can kind of keep up. You just have to have enough valid work available for the GPU to do, or from each streaming multiprocessor to do, so that you never have to actually feel that full latency. But for that reason, if you write a single-threaded CUDA application, it's going to be much slower than the equivalent CPU implementation, because the CPU is really kind of organized about how can we make the most out of our cache hierarchy, how can we get the very best cache performance back out. You have processors now with 128 megabytes of cache on chip and things like that. Here we still have kilobytes of cache for each streaming multiprocessor's perspective. For one thread's perspective, it's going to perform much worse. We just have lots of threads. Now we're talking thousands and thousands of threads, so that the number of warps is such that we always have a warp available. So again, going back to the question, as a programmer, do you need to be aware of this? Well, I think in a sense you do, unless if you're satisfied with that 90% kind of performance, then maybe you don't need to ultimately know that. But there are tools then available that allow us to kind of reason about how effectively we're making use of our warps in a particular application, and can we avoid this kind of problem and the other versions of this kind of problem. Because presumably, again, we went from, 16 registers per thread to 17 registers per thread here. So we went from 4 blocks executing in parallel to 3 blocks executing in parallel, and these were all kind of made up numbers anyway, but it was 4,000 threads to 3,000 threads, right? 4K threads to 3K threads executing here in parallel, and the number of warps then also drops by that same ratio, right? So the likelihood of there being nothing available to schedule at any given point in time, and we have to basically stall, we have to wait for something to return back, is going to be roughly that percentage higher likelihood here than it would be in this example here. So that one register can potentially make a difference. So I think I covered all of this here in that, the whole idea of this SIMT type of model, and again, warps are referring to a technology from old school looms and weaving, and it's kind of a parallel threaded technology, but it's really just a play on words, so I don't want to focus on that too much. But in terms of what's actually getting executed over time here, it is depending on what is happening in terms of what warps are able to be executed and what warps have to wait for a certain period of time. But at a high level, this visualization is a good way to think about it, where we have warp 8 and it's on instruction 11 and it succeeded. This diagram at least strongly implies that if you're on warp 8 instruction 11 and you got all the way through the instruction to the write back phase, that it still goes back to the ready queue for scheduling later. You don't get to go on to the next instruction right away. So we go from, say, warp 8 instruction 11 to warp 1 instruction 42, etc. And then eventually we move on and we get back to warp 8 instruction 12 and continue on from that point, depending on what's happening inside those threads for that warp. And still, the performance, even though they're no longer entirely in lockstep, all the different threads in your block, the performance of your instruction cache is still going to be pretty good because they're all still executing the same kernel. It's only these 32 threads that are guaranteed to be on the same exact instruction, but all these are still executing from the same instruction memory stream here. So that switching, that time to go from warp 8 to warp 1 should be effectively zero overhead. All we are changing is a program counter and that other kind of data about what thread we're on. Those constants that we looked at in the kernel of thread index.x and thread index.y and thread index.z, you need that, and you need the program counter that you need to kind of swap out. And that presumably, although it's an implementation level detail, that presumably is going in some read-only data cache, and it's just there and it's available for each warp to take advantage of. Or it's just the actual data structure that the warp scheduler itself, assuming that this is a FIFO queue of some sort, that's the actual information. When I say there is a thread warp being available to schedule, FIFO queue kind of makes sense if I were to implement this. The size of that queue for each entry in the queue would be a function of what is the actual metadata I need to keep track of to go from warp 7 to warp 8 to warp 3 to warp 4 in that diagram. think at least a program counter, then just the index information. And possibly, we talked about the register file, whether that gets calculated or whether that's just also kind of a constant offset that's included with the thread warp. Either way, some way of keeping track of that is also what's going to be stored in there. But that's pretty much it, and that's why it's kind of zero overhead. You compare that to the context of a modern, operating system resident thread or process that you want to swap out with your OS scheduler. There, we need everything to be able to get back to where we were in terms of the thread execution. We need to have, basically, we either flush it to memory or we have the entire contents of the register file. We have to have all the flags of execution of where it's at, as well as in addition to the program counter. There your thread swapping time could be in the high order microseconds or low order milliseconds for swapping that out. Here, going from thread warp 7 to warp 8, depending on whether you think of it as 4 cycles to fully insert or 0 cycles for that first or 1 cycle for it, it's basically a zero overhead swapping between them because there's just very little information that has to change. I wanted to do this as an exercise, but that question as I read it this morning is very open to interpretation. The answer is a lot. We'll leave that as the answer to that question. Because there is kind of this yin and yang of you want to have more threads, but those threads are going to have the load instructions at the same percentage as the other threads you may have already previously had. So there is no guarantee you can always fully tolerate and hide the memory latency. But if you have a sufficient number of warps in the ready queue available at any given time, you can estimate how many do you need to have given a certain load store or cache request rate here, how often you're going to have to tolerate that full memory latency. Again, that also is still kind of saved, and it's not as bad as it may sound, because even with small data caches, just like we can tolerate the small instruction cache, we can oftentimes tolerate a relatively small data cache. Again, that now depends on how you write your kernel, but I don't have the vector add example up anymore. But for the matrix multiply, as we're doing our loads and stores from locations in memory, you write it from a single thread's perspective true, but you're not doing so arbitrarily, right? I want this element on this thread, the next thread's going to have the next element, the thread after that's going to have the element after that. That would lead to pretty good spatial cache performance, right? The locality we would have we maybe miss on the first warp, but then maybe the next warp already has its entries available because likely as we allocate our warps, they're kind of being done sequentially, spatially, effectively, and so our memory access pattern, if we write it in an appropriate way, should have reasonably good performance as well. So given the hardware limitations of how many registers we have total, and some other kind of physical limitations in terms of how many threads is the upper limit for a given streaming multiprocessor, or how many total blocks can I have in a given device. And those are all kind of arbitrary, but I think given a limit of, okay, I can have 2 to the 32 minus 1 blocks per grid on that device. Okay, I'm telling you that's the hardware limitation. Okay, there's a 32-bit register somewhere that's storing that information, right? That's why that's the limitation. They would support more, but they would need a 33-bit register. So they made a choice of 32-bit. That's why that's the limitation. Why is there a limit of just 256 registers per thread, or 255, registers per thread on that device? Why would we think that's the case? Think back to 381. By the way, 255 is not an absolute ton, but it's more than the 32 or 31, depending on your perspective, we had in 381. What would the limit here be? We know it's not the size of the register file, right? That thing's massive. Why is it limited to 255 per thread? Yeah, not just an 8-bit address. You're right, 8-bit address. We have to think about the actual instruction itself, how the instruction itself gets encoded, and you only have so many bits for that. And that's a design trade-off we make, right? Given a certain number of bits or total number of registers, we have to have a certain number of bits for the register addressing fields in the actual instruction itself. My interpretation of that limitation of that device is we have 8 bits for source 1, 8 bits for source 2, and 8 bits for destination. You don't have a lot of extra, and if it's a 32-bit instruction, which I think is the valid assumption for these architectures, you don't have a lot of extra bits to use just for opcodes and things of that nature. Why 255 and not 256? What do we think? It's okay. Think about it later. I think it's semantics. There's probably a 0 register as well, similar to what you would have had in MIPS. And there may be some other mechanism by which that 0 gets used that doesn't require actually considering it a separate allocated register here. So there are these limits, I guess, is one way to think about that. And the limits do vary quite a bit depending on what device you are supporting. NVIDIA likes to think of things in terms of what version or iteration of compute capability your device has, but there's a direct one-to-one correlation between what actual physical device you bought and what compute capability it has. But there are these physical limits. And so part of your job as the CUDA programmer versus just someone just writing C or Python code is, again, the kernel itself is its own kind of separate thing. But now for the device I'm going to be executing on, what is the best way to take advantage of the resources I have? Or another way to think about that is, what is going to be the limiting resource for this kernel that I'm currently working on? Conventionally, the approach for determining what your limiting resources were was referred to as the CUDA occupancy calculator. It is just a spreadsheet. It's a clever spreadsheet, but it is just a spreadsheet. There are now today ways to do that via your code as well. There are CUDA library calls that let you determine occupancy to determine where there may be some inefficiencies. But it can be kind of fun to look at that and see what kind of hypothetical scenarios for your given application here. So I do have it open. It is literally just a spreadsheet that will tell you effectively for a given application what is the limitation of that kernel on your particular device here. So you would first select basically compute capability. They don't want you just to select the device, I guess, but you're saying, okay, here's the device that I'm going to be running on. The one on that machine I've been remotely accessing, I think, is device 3.5, just to give an example here. And somewhere we have to specify, that would be per device, the shared memory configuration size in bytes, and I don't actually know. It should be a drop down here of, okay, we bought the high-end device. And then that's specific to your device. So I'm going to be running on this GPU. It's of this version, basically of this generation, or they call it compute capability. Now for this next set of boxes are, now for your application. What is your application actually requiring here in terms of these 3 parameters? Basically just these 3 parameters. It doesn't care about dimensionality of your threads as such, but more so how many threads are there in each block you have here. Then how many registers there are per thread, as well as we haven't talked about how we access the shared memory, but how much shared memory we have per threads. And you can directly access that information. I don't know if I even have this open, but you can look at any executable. That got messed up. One second. Any executable that you compiled, and it will tell you, it's a little, they don't necessarily make it easy to read necessarily, but for any executable you specify, it'll tell you exactly for that kernel how much of those resources is it actually using here. So for example, this kernel is using 42 registers in it. There is probably no way to look at the actual kernel itself directly and get that answer and say, oh yeah, this is using 42 registers. It is also using a certain amount of shared memory, which is one way to alleviate the cache issue, right? We copy into this separate software managed memory, and we're not worrying about the cache as such. And it's also telling me how much of that it is using for this kernel's implementation. It's also telling me how many bytes, I believe, of constant memory it is using as well for some of that metadata associated with each individual thread here. And that's what we would plug in into our occupancy calculator to tell us, okay, given that, how many of these things can I fit on an SM at any given time? How much occupancy do I have? So I can do that. Threads per block is, I don't have, that's not listed here. that would be in the source code itself directly, how many threads per block I specified here. And I didn't make it that easy. Here you specify, so it depends. The application allows you to decide how many of these you're executing, so I need to find a main here and find the same default here. 32. Didn't make this easy. Give me a second. 5 times 2 times 32. Sounds good to me. 320 by 320 by 320. But that's fine. Then that must be running on a much higher compute capability. I'm wrong on the number here. That wouldn't work. So 320 by 320. Okay, we can try it. That seems really high to me, but that's fine. Oh, sounds good. Registers per thread was 42. And shared memory, what did it report back out? It was using for shared memory 8192, or depending on which version of the application we were looking at. And this will then tell you what the occupancy can be, meaning how many warps can it fit on that architecture in parallel at one given time. That's not exact, and this is called occupancy. It's not saying CUDA performance calculator. That'd be a much harder thing to model via a spreadsheet. You can use profilers just like you do in conventional systems to do performance profiling, related but not exactly the same as occupancy, right? Occupancy just tells you how many of these warps, going back to the diagram here, how many of these things do I have available at any given time, such that when I have to put a warp in timeout, what is the likelihood I'm going to have other warps available to keep doing good work? So in that sense, I think generally it's correct to say more occupancy is better than less occupancy, because you're just increasing the potential underlying efficiency of the implementation, but it's not the same as performance. So it's not a guarantee of better performance, but it's one way to look at the efficiency of your application. And it then tells you, for a given compute capability, what are some of the kind of hardware limitations, I'll make this a little bit bigger here, of what can actually be supported. And for this example here, right now we're at 100% occupancy of each multiprocessor. That's a very large thread block, I'll just say. So here are some of the limits we have here. 32 threads per warp, so that's a hardware limitation. I think if I change it, I can get a different number there, but for now we're on a version that has 32 threads per warp. Here's just the maximum number of warps per multiprocessor. So that also tells you 1024 is the maximum number of threads per multiprocessor at any given time. So for this compute capability, if you can get 32 warps going in parallel, you've done your job. Limited by 16 thread blocks per multiprocessor. So that gives you an upper limit on how many threads you'd want to have per thread block here. Registers per multiprocessor. Shared memory per multiprocessor, which we actually specified here. Register allocation unit size, so maybe there's a limit per block that you have to give it at least 256 registers per block at a time in units of 256. That could probably make some sense. Thinking about the underlying hardware, that probably eliminates a multiplier. If you keep it a power of 2, you can do some shift logic versus having to have a multiplier in there. And then it tells you, for the things you specified for your application, what is potentially the limiting factor here. In this case, it's just limited by the maximum number of warps, which is 32 here. We have a very large number of threads. If instead, and again, threads per block is really large here, so let's lower it to something more common like 256 threads per block here. And now we can start to see other limitations here. With 42 registers, that's not a limitation. But just like in the example we showed at a very high level, if I were to go up to, what does that number look like? It's, let's say, 70 registers per thread. Then we got dropped down on our efficiency, and we went from being able to execute 32 warps, in parallel to 24 warps in parallel here, just by increasing the register count that we had here. Similarly, if we go back to where we were in terms of registers per thread, but instead recognized that I actually want to increase the number of threads per block here. All right, 256 threads per block was good. Let's go up to 320 threads per block here. Our efficiency actually went down, which now that starts to become a little bit counterintuitive here in terms of what was the limiting factor, because we're just limited by the total number of warps we can support at a given time. So it turns out it's not as straightforward as just larger is better. I think it's more of an issue of this, if it's not a multiple of 32, although 320 certainly is, if it's not a power of 2 multiple of 32, you're not going to be guaranteed to have full efficiency on that particular device here. Again, this type of tool and using this kind of tool will not tell you that, yes, this application with a kernel launch is going to be higher performance than this other potential kernel launch parameter, but it'll give you some insight as to what percentage of my GPU per SM is actually being executed here. And it lets you answer these kind of questions. And we can leave this as one of the last things we'll do today. So for this example where I kind of just copied a subset of the spreadsheet for compute capability 3.5 here, old but still relevant in terms of devices people still use for GPU compute. Assuming we had an application that had 382 threads per block and 9 registers per thread and 4K bytes of shared memory per block, how many blocks could we run simultaneously, and what would be the limiting factor or factors? Take a minute. Wake up the person next to you or nearby if needed. What would be the limiting factor? Of course, with the spreadsheet, I could just type that in. So we can do that if we want to, but can we reason about what's happening here given the physical limits for GPU compute capability 3.5? So just for example, the limit is 16. That's the maximum number of thread blocks that are allowed to be scheduled in parallel on a multiprocessor. So the answer is less than 16. Okay. With 382 threads, how many warps would there be per block? Don't make me get out the spreadsheet. We can figure that out. You have to round it up, presumably. Because that's 60 and it winds up being 64. Wait, 12 would be, what do you get, 11.9? Yeah, so 12. 12 warps per block here. So that's our second limitation we already knew. From a hardware perspective, 16 blocks had to be our upper limit. We have 12 warps per block here. So now we're looking at no more than 5, right? No more than 5 blocks going on here. If we had 5 blocks, you have to kind of keep working forwards and backwards here, I guess, right? If you had 5 blocks, we'd be okay from a shared memory perspective. We could fit 5 blocks on here. 9 registers, not even doing the math, that should be more than fine, right? We were talking about 40 or 60 or 70 being a limiting factor here. So that would be your limiting factor. Just the total number of warps that could be supported here. I'm not even going to plug that into the spreadsheet. I trust our math here. Shared memory looked like it could have been a limiting factor here because that's a large amount of shared memory. But doing the math, you would need, upwards of 12 blocks to be able to support that. We can't even get close to that because of our limits of how many threads we can support at any given time here. I said 16 thread blocks, limited by 64 warps here, 12 warps per block, but the total number of threads per multiprocessor is also limited to 2048. But this many thread blocks would limit us. So that number of 12 warps per block, the math is the same. It's just that 32 times 64 anyway. So that same number still would apply. So that would give us 12 warps per block. We can only support then 5 blocks per streaming multiprocessor. I was trying to do the math via threads, but it's going to give us the same result here, I believe. And finally, I think it's good to inspect the assembly to know that I think we're seeing microarchitecturally there isn't anything that new or that crazy here. But when we look at what the PTX virtual assembly format provides us, it is some combination of our RISC style, 381 style assembly, as well as then support for all of the shader type stuff we've also had to be able to support, right? So it's kind of a hybrid of both because it's kind of serving both purposes here, right? So you have just support for basic 32-bit math via this ISA, as well as then all the kind of special instructions that you have here. So this was, and I just compiled it beforehand, for this matrix multiplication CUDA kernel, which is what's being shown here. There's some shared memory going on, but the underlying assembly is itself, it's auto-generated, so it's not as clean as if you had written the assembly yourself. But what you're going to then have are a series of instructions that don't look that different from your MIPS style instructions. So loading some of our parameters, kind of our per thread parameters here via load instructions, multiplication instructions, shift instructions, add instructions. This is something that is new unless you've studied kind of old school ARM architecture. Setp.gt, that stands for set predicate. So instead of having all sorts of different branch type of instructions, branch less than, branch greater than, branch equal, you would then have an architecture that just supports a single type of branch instruction, just called branch. And instead of then having different opcodes for the different types of branches you'd want to support, you'd have a separate instruction that's basically set condition code, or in this case, it's called set predicate, which is set predicate given a 32-bit signed 32-bit integer comparison if it's greater than. Set predicate called P1 if register 39 is bigger than register 32. Probably too much for us to dive back into the CUDA and know for certain why it's exactly doing that at that point. But presumably at some point inside my kernel, there is a branch instruction. There's not an if statement, but there's a for loop, right, which includes less than or equal to, could get compiled as a greater than, right, so that it's going to get out of the loop if it's not needing to continue inside that loop. And given that predicate of P1, only if that predicate is true, execute a branch instruction. And that's one mechanism by which we can do branches. But the cool thing about these predicates versus just traditional ALU codes or comparison codes is you can actually predicate any instruction. So the most common use for this would be to predicate just the branch instruction. I'm only going to take that branch if the greater than condition for register 39 and 30 and R2 is true. That is equivalent in MIPS to branch greater than, right? That's effectively what we've set up via those two instructions. But while other architectures just use condition codes for that branch scenario, these predicates could be applied to any instructions. So we talked about how when we have these threads inside our warp, and all 32 of them are required to execute in lockstep, how do I support an if statement? How do I support maybe half the threads having to go left, true branch, half the threads having to go right, take the false branch? You can do so via explicit branch instructions, but in terms of for threads inside a warp, you can do so also via this so-called predicated instruction execution, where you're not just predicating a single branch, you're predicating as many of these instructions as you'd like going forward. It would be equally valid assembly to predicate a whole block of instructions so that only the threads for which that condition was true are actually going to execute that instruction, but they're all going to go through lockstep. So they're all going to do fetch, decode, and all those steps. Only for the instructions in which that predicate was true would it actually write back the results of that instruction. So it's wasteful in a sense, right? You have threads in a warp. Do they take the left branch or do they take the right branch? And the answer is they always take both. So we kind of serialize our branches. That's how our assembly code gets generated anyway, right? But now we're actually executing both branches for all of our threads. And one mechanism by which we can manage these threads inside a warp is to then have, for every branch we set that predicate and only the instructions for which the predicate is actually true. This is where the actual divergence would happen in your code. For some instructions, R39 would be greater than R2. For other ones, it would potentially not be. They all still do those instructions. Only for those in which it's true do we actually continue with that execution and actually commit the results into the register file or do whatever the instructions require to do for those threads. Let's leave things here for today. Thursday's kind of it. We should celebrate. I don't know what we should do. But it's it, and then we have next Tuesday, and I'm just very excited to see what you're able to come up with. So let's leave things here for today, and see everyone on Thursday.